So in this session, we will now do the second part of our review for the first exam. So let's go. So let's start with our first problem here. Determine whether the sequence is convergent or divergent. If it is convergent, find its limit. And if it is divergent, give a brief explanation. So in here we have the sequence with terms a sub n, which is equal to 4 raised to n minus 1 over 3 to the n plus 5. So it looks like this is a geometric series, except that on the denominator, we have a plus 5. So what we're going to do is the following. We will define a sequence. We define the sequence Bn, which is just the reciprocal of a sub n. And therefore, this is equal to 3 to the n plus 5 over 4 to the n minus 1. Okay? Or if we now separate this into two fractions, this will be 3 to the n over 4 to the n minus 1 plus 5 over 4 to the n minus 1. Okay, so what we're going to do is to show or to find the limit of this Bn. And once we know the limit of Bn as n approaches infinity, we will be able to find the limit of 1 over an, and therefore we will get the limit of a sub n. Okay, now let's label this as our a, and then this guy here as our b. Oops, let me use other letters since I have been using an and bn already. But let me just call this guy here, say K. And then this guy here, let me just call this L. So for K, we have your 3 to the n over 4 to the n minus 1. We can rewrite this as 3 to the n over 4 to the n over 4. Or simply, this is just 4 times 3 over 4 raised to power n. Okay? Now, since 3 over 4, this is less than 1, the limit of this exponential expression here will go to 0 as n approaches infinity. Okay? The limit as n approaches infinity of 3 to the 3 over 4 raised to n, this is equal to 0. Okay? Also, for L, definitely if we find the limit of 5 over 4 raised to n minus 1 as n approaches infinity, the numerator is constant, the denominator goes to plus infinity, so this is also equal to 0. Which means that the limit of b sub n as n approaches infinity, this is equal to 0. Okay? And since all the terms here are positive, this limit here actually goes to 0 from the right. Correct? Thus, we now have the limit as n approaches plus infinity of 8 sub n. This is equal to the limit as n approaches plus infinity of 1 over b sub n. This is equal to plus infinity. Okay? Therefore, this sequence here is divergent. So a sub n is divergent. So this is one way to solve or to determine whether this guy here is convergent or divergent. Another way is, well, you can define your a sub n as a function of replacing n with x. Then you can apply your L'Hopital's rule. And still you will get plus infinity. Okay? So let me remark that. Also, one can use use L'Hopital's rule to determine to show that limit of an as n approaches infinity, this is also equal to plus infinity. Okay? Okay. So, there is a question. So, sufficient na po ba sabihin na yung numerator mas mabilis tumaas kaysa sa denominator? On an exam, it's not enough. You have to explain why 4 to the n minus 1 is faster than your 3 to the n. And to show that, you have to find the limit. You have to use that rule that we used in here. Okay? Okay. So that's for our first problem. For second problem, so our sequence is ln of 2 to 2n squared plus 3 minus ln of 4n squared minus 3. So for this guy, let us just rewrite an as a single logarithm. So this is just the logarithm of 2n squared plus 3 divided by 4n squared minus 3. And now we can find the limit, okay? So if um, if limit or if f of x, this is equal to ln of 2n squared minus or plus 3 divided by 4n squared minus 3. Sorry, I'm using x, so I'll have to replace this with x. Then the limit of f of x as x approaches infinity, this is equal to ln of the limit of 2x squared plus 3 over 4x squared minus 3, right? As x approaches infinity, this is now equal to ln of 2 over 4, or this is equal to ln of 1 half, or maybe you can also write this as negative ln of 2. Okay? Now, take note that this part here is necessary so that when you find the limit of the function as x approaches infinity, you can bring it inside the logarithm. Take note that you can only do this if you have a continuous function. Okay? So that's why we define a continuous function instead of working only on the sequences where the domain is just the set of integers. Okay? So in here, limit as n approaches plus infinity of a sub n, this is also equal to negative ln of 2. Questions? Let's go to our next problem. Okay, so there is a question. Can we end at ln of 1/2? Yes, you can end at this ln of 1/2. Now, for this, determine whether the sequence is convergent or divergent. If it is convergent, find its limit, and if it is divergent, give a brief explanation. Okay, so in here you have a sub 1 equals 1 and a sub n plus 1. This is equal to 2 over 5 times 3 a sub n minus 2 for n greater than or equal to 1. So this is a recursive formula. So the term depends on a previous term. So how do we do this? What we can do is the following. We say let L be equal to the limit as n approaches infinity of a sub n. And this is also the limit as n approaches infinity of a sub n plus 1. Okay? So, if we get the limit of this guy, this is equal to the limit of the other guy. So, the limit as n approaches plus infinity of a sub n plus 1, this is equal to the limit as n approaches infinity of 2 over 5 times 3 a sub n minus 2. But again, from this assumption, left-hand side is just L. The right-hand side will be 2 over 5 times 3L minus 2. And then you can just distribute this 2 over 5 over this sum or difference. We'll get 6 over 5L minus 4 over 5. Okay? And then from here, all we need to do is to isolate L. We just solve for L and we'll have the limit. So in here, we will get 6 over 5L minus L. So I'll bring this guy here to that side. And then I'll bring negative 4 over 5 to the left-hand side. And then I'll switch the equality. So this is equal to 4 over 5. And then 6 over 5 minus 1, that's just 1 over 5. So we have 1 over 5L. This is equal to 4 over 5, which gives us L equals 4. So this is the limit of this sequence. Okay? Questions? Okay, let's move to our next problem here. So this time, let's look at series. So determine whether the following series is convergent or divergent. If it is convergent, find its sum. And if it is divergent, give a brief explanation. So in here, we actually have difference of two geometric series in here. So we can just apply um, the geometric series formula, correct? So this guy, this series here, we rewrite as the sum as n runs from 1 up to plus infinity of 3 over 2 to the n minus um, sum n from 1 to plus infinity 1 over 2 to the n plus 1. So the equality here, um, at this point of the solution, the equality here, um, uh, it's not yet um, determined, okay? But we'll just write it. So um, let me put the quotation marks, okay? Take note that you can only separate the two guys, the two guys, the two summations here if you are sure that the limit exists, okay? So since we are still solving whether this the limit of the partial sums here exists, let's just put those quotation marks. But we will find after the computation here that both series here converge, and therefore we'll be able to find the sum using geometric series formula, and therefore we will have the equality. The equality will be confirmed. But anyway, we have the series from n equals 1 to plus infinity of 3 over 2 to the n. So this guy, we will adjust, especially the index, because we can only apply, recall that you can only apply the formula a r to the n if n starts from 0 to plus infinity. And this will be a over 1 minus r. So we need to adjust. The index must start at 0, or the power of your common ratio must start at 0. But this guy here, the common ratio, the power of that common ratio starts at 1. So we have to rewrite this series here as sum n from 1 up to plus infinity of 3 over 2 times 1 over 2 to the n minus 1. Okay? Or this guy, let's just rewrite it this way. Sum from n equals 1 to plus infinity of 3 over 2 times 1 over 2 raised to n minus 1. Okay? So now the common ratio starts, the power of the common ratio 1/2 starts at n at 0. Okay? Because we have here n minus 1 and n starts from 1. So the power starts at 0. And since r, which is 1/2 in absolute value, is less than 1, one can apply the formula. Let me write this guy here, formula star, if r in absolute value is less than 1. So one can apply the formula star, this star here. So continuing, we have now 3 halves over 1 minus 1/2. But this is just 3 halves over 1/2. So this is just equal to 3. Okay? So that's the first one. For the second one, we have the sum 1 over 2 to the n plus 1. And from 1 up to infinity, we rewrite this as the sum from n equals 1 up to plus infinity of 1/4 times 1/2 raised to power n. And then same explanation or same reasoning as in this guy here. This series is now equal to 1/4 times 1 over 1 minus 1/2. And this is equal to 1/4 times 2, which is equal to 1/2. So both series converge, and we have the sum, the actual sum for both of them, and therefore we will get the actual sum of this original series. So therefore, the series from 1 up to plus infinity with terms 3 over 2 to the n minus 1 over 2 to the n plus 1. This is simply 3 minus 1/2, and this is equal to 5/2. Okay? So there is a question, bakit 1/4? Tignan mo yung power ni 2. Power of 2, it's n plus 1. And you want n minus 1 power. So you have to bring out 2 2's or 2 squared. And 2 squared is 4. That's why we get here 1/4. Oh, in this guy here, sorry, in this guy here, the power is n minus 1. Maybe that confused. Yeah, this guy here must have power n minus 1 so that we can apply this formula. Okay. Other questions or clarification? Next, determine whether the following series is convergent or divergent. If it is convergent, find its sum. If it is divergent, give a brief explanation. So I think you're familiar with this type of questions, particularly this question, because this appeared in one of your homeworks. But anyway, let's just work this out. Let S sub k be the sequence of partial sums. Okay, so this will be at n equals 1, you will have tangent inverse of 3 minus tangent inverse of 1 plus at n equals 2, you have tangent inverse of 4 minus tangent inverse of 2 plus at n equals 3, you have tangent inverse of 5 minus tangent inverse of 3. Let's add some more. Plus at n equals 4, you have tangent inverse of 6 minus tangent inverse of 4. And then plus you have tangent inverse of k plus 2 minus tangent inverse of k. Okay? And then in here we see that this guy here, tangent inverse of 3 will cancel this guy. So let me put this as 1. And then this guy here will cancel this guy here. Let me put this as 2. And then if we added one more term in here, where n equals 5, the tangent inverse of 5, the minus tangent inverse of 5 will cancel this guy. Okay, so it will cancel this guy on the third term, etc., somewhere here. And then what part will be canceled here? The tangent inverse of k. So notice that this guy here will be canceled. Okay. To see that, let's check. Let's write some previous terms. So in here, so this guy here, it's k, it's n equals k. So for this guy, you have k minus 1. Tangent inverse of k minus 1. And then in here, and then for this guy, you will have k minus 1 plus 2. That becomes k plus 1. Tangent inverse of k plus 1. So this was the previous term. Okay. And then on the previous term, more previous term, you have your k plus 2 or k minus 2. So you will get here the k minus 2 term. So you have that tangent inverse. And then the minus here, you have your tangent inverse of k. Okay? And then let's just put the plus here. So notice that this guy here will cancel that tangent inverse k in here. So the minus part, the minus part will cancel the plus part of the previous two terms. So this is the first term. Say this is your last term, second to the last, second to the last, and then third to the last. So the minus part will cancel two terms before, the plus part of the two terms before. So this guy here will cancel the previous terms here. Okay? So this guy here will cancel the term previously. This guy here will cancel the term also previously. But in here, the one that will cancel this guy is the next term in here. Okay? And then of course, the one that will cancel this guy is two terms after this. So 1, 2. Therefore, your S sub k here will be simplified into, you have your tangent inverse of k plus 1. You also have your tangent inverse of k plus 2. And then you have here your tangent inverse 1. So minus tangent inverse 1. And then you have here the minus tangent inverse 2. Okay? So you want the limit or the sum, and from 1 up to plus infinity of tangent inverse n plus 2 minus tangent inverse n this is equal to the limit as k approaches plus infinity of s sub k. And then this guy, what's the limit? Remember the graph of your tangent inverse. So this guy here will go to pi over 2 plus this guy here will go to pi over 2 also. Tangent inverse of 1, that's pi over 4. So you have minus pi over 4. And then this guy here, not so special, so let's just write it as tangent inverse of 2. And therefore, we will have what? 3 pi over 4 minus tangent inverse of 2. So this is the sum of this series here. Okay? Next problem. Determine whether the following series is convergent or divergent. If it is convergent, determine if it is absolutely or conditionally. If it is divergent, explain why. Okay? So in here, look at the difference between the problem here and the previous problem. For the previous problem, if it is convergent, you need to find the sum. So you should have a way in finding the actual sum. On the other hand, you may or may not be able to find the actual sum if it is convergent. However, you have to say if it is absolutely convergent or conditionally convergent. Okay? So, what are we going to do with this? Look at this. Your 2 plus sine n. Look at this. Now, since sine n in absolute value, this is less than or equal to 1, 2 plus sine n, okay? 2 plus sine n, let me adjust this. This 2 plus sine n is greater than 1, greater than or equal to 1, but less than or equal to 3. Okay? Now, what we're going to do is to show that this is divergent. So if this is divergent, we need to, well, we can use comparison test. And we will compare this series with the series 1 over n ln of n. And I know you're familiar with that series already. We've done that, okay? Remember that when you apply comparison test or limit comparison test, you should have uh, a big database of series, okay? So in here, so 1 over n ln of n, this is less than, okay, or equal to 2 plus sine n over n ln of n. And take note that this is greater than 0 since n starts from 2. So let us write that for n greater than or equal to 2. Okay? So now, we show that the series n from 2 to plus infinity of 1 over n ln of n, we show that this is divergent. Okay. We use integral test. So we use integral test. Okay. So let f of x, this is equal to 1 over x ln of x for x greater than or equal to 2. Then f is decreasing since as x increases, x ln of x also increases. Okay? And so 1 over x ln of x decreases. And we already know that this guy here is positive. Also, f is positive on the interval 2 to plus infinity. Thus, integral test is applicable. So, we apply now integral test. So, we integrate from 0 to plus infinity 1 over x ln of x dx. This is equal to the limit as t approaches plus infinity. Take note, this is still improper integral, so you have to use the definition of the improper integral. Don't forget to write the limit part here. So this is the limit as t approaches infinity of the integral from 2 to t of dx over x ln of x. And then in here, let's just write u equals ln of x, du equals dx over x. That will be the substitution that we will use. This is the limit as t approaches plus infinity of the integral when x equals 2, u equals ln of 2. And when x equals t, u equals ln of t. And this guy here, this is just du over u. Still following? So this is equal to the limit as t approaches plus infinity, ln, absolute value of u. Okay? And we evaluate this at u equals ln of 2 and u equals ln of t. And this guy gives us the limit as t approaches plus infinity of ln of absolute value, ln of t, minus ln of 2. And as t approaches plus infinity, ln of t will go to plus infinity. We get the absolute value. Ln of something going to plus infinity will still go to plus infinity. Okay? So, continuation here. The proper integral is divergent. The improper integral is divergent. By divergence test, by integral test, the integral 1 over n ln of n from 2 to plus infinity is divergent. Therefore, by comparison test, the original series is divergent. Series 2 plus sine n over n ln of n from 2 to plus infinity, this guy is divergent. Okay? Okay. So, there is a question. Sir, kaya ba, ano yan? Pwede bang gamitin divergence test from the start? Gamitin mo, pero hindi naman mag-work yun eh. Tama ba? Because the limit of the terms, it will go to 0. And if the limit of the terms go to 0, divergence test is inconclusive. Correct? So question, paano siya mag-0? Well, as n approaches infinity, your n and ln of n will go to plus infinity. And your numerator, it's just between 1 and positive 3. So whatever the constants in the numerator, your denominator still goes very large. You can use your squeeze theorem. Correct? So the limit will go to 0 ng mga terms. Okay? So, this is the complete solution and there's no shortcut. Bawal mag-shortcut pagdating sa exam. So, pansinin nyo kung paano natin ginawa. Okay? Pansinin, at least itong solution na to, pansinin kung paano ginawa. Gusto natin gumamit ng comparison test, maghahanap tayo ng pwede nating ipang-compare. Okay? And then, nakahanap tayo ng pang-compare. Kailangan natin malaman kung divergent or convergent. But since ang gagamitin natin ay yung mas mababa, kailangan natin ipakita na divergent. Okay? And para ipakita na divergent ito, we've done this a lot of times, kailangan natin gamitan ng integral test. So, pakita natin lahat ng conditions para ma-apply yung integral test. We have decreasing part and we have positivity. Okay? And therefore, we apply integral test. We apply improper integral now, or we use improper integral now. And once we're done with the improper integral, we look at how we state all our conclusions. Okay? So that's for this example. Next, determine whether the following series is convergent or divergent. If it is convergent, determine whether it is absolutely or conditionally. If it is divergent, explain why. So for this, what we're going to do, so we have here sum n equals 2 to plus infinity of n, tangent inverse of n over n cube plus n plus 3. Okay? So to do this, for n greater than or equal to 2, we know that tangent inverse of n will be less than pi over 2. So, kailangan nyo alalahanin yung graph niyan ng tangent inverse. So, this is your pi over 2. Tangent inverse is something like this. And of course, you have something below here. Asymptote is negative pi over 2. Okay? So, you have to remember that. So, as n, for any n greater than or equal to 2, tangent inverse of n will always be less than pi over 2. So, mula dito, may isip nyo na kung ano yung gagawin nating comparison. So, your n tangent inverse of n, this is over n cubed plus n plus 3. So, in here, so for n greater than or equal to 2, this expression here will be less than n over n cubed plus n plus 3. And furthermore, since nag-add ka ng number sa denominator, ng positive number sa denominator, mas liliit yon. Tama, yung fraction. So this will be less than n over n cubed. And n over n cubed, this is just 1 over n squared. Therefore, we compare this. Okay, we compare this with the series with terms 1 over n squared. And furthermore, pakita natin na absolutely convergent itong part na to. Okay? Absolutely convergent itong part na to. So, here, now, the series. So now, consider the series n equals 2 to plus infinity of the absolute value n tangent inverse of n divided by n cubed plus n plus 3. And take note also that this guy here, this is always positive. So yung absolute value, wala naman talaga siyang effect kasi positive talaga yung terms. So you're basically calculating this series also. But anyway, this is less than the series 1 over n squared and from 2 to plus infinity. Since this series 1 over n squared and from 2 to plus infinity is a p-series. P-series with p equals to 1 over n squared and from 2 to plus infinity is convergent. Okay? And therefore, this guy here is convergent. So, the series absolute value n tangent inverse of n over n cubed plus n plus 3 and from 2 to plus infinity, this is convergent. Therefore, the original series without absolute value, which is exactly this guy, okay, therefore, n tangent inverse of n over n cubed plus n plus 3, the series of these terms, or the series with these terms, this guy is absolutely convergent. Okay? Questions? Okay. Next problem. Determine whether the following series is convergent or divergent. If it is convergent, determine if it is absolutely or conditionally. If it is divergent, explain why. So first, in here, we can rewrite this as the series from n equals 1 to plus infinity. You have cosine n pi. Okay, cosine n pi. N is an integer. N runs from 1 up to plus infinity. So cosine n pi, it's just negative 1 to the n. Take note, when n equals 1, you have negative 1 here. And therefore, when n equals 1, negative 1 raised to 1, that's still negative 1. And then in here, on the denominator, you have square root of 2n squared minus 1. So first, the series is alternating. Okay, with bn equals 1 over square root of n squared minus 1. Okay? So we show what are the conditions so that we can use alternating series test. We show that bn is always positive. We also show that bn is decreasing. And we show that bn goes to 0 as n goes to plus infinity. Correct? So let's just state those. For n greater than or equal to 1, 2n squared minus 1, this is greater than 0. Correct? And so bn equals 1 over square root of 2n squared minus 1. This is also greater than 0. This guy here tells us that square root is defined. Correct? And then since we just get principal square root, we just get positive values. So you have positive bn's. Now, as n increases, square root of 2n squared minus 1 also increases. So bn decreases. Finally, we get the limit as n approaches plus infinity of b sub n. This is the limit as n approaches plus infinity of 1 over square root of 2n squared minus 1. This is equal to 0. Therefore, by alternating series test, the series cosine pi n over square root of 2n squared minus 1, and from 1 up to plus infinity, this guy is convergent. So it is convergent. We are left to show if it is absolutely or conditionally convergent. However, or now consider the series with the absolute values, cosine of pi n over square root of 2n squared minus 1, and from 1 to plus infinity. But this is just the series from n equals 1 to plus infinity, 1 over square root of 2n squared minus 1. So what we're going to do is we use LCT, limit comparison test, and compare it with the harmonic series, 1 over n from 1 to plus infinity, which is the divergent harmonic series. Okay. Now we take the limit of 1 over n all over 1 over square root of 2n squared minus 1 as n approaches infinity. This is equal to the limit as n approaches infinity of square root of 2n squared minus 1 over n. But this is also equal to the limit as n approaches plus infinity of square root of 2n squared minus 1 over n squared. And check that this is just square root of 2 as n approaches infinity, which is greater than 0. So, the series absolute value of cosine of pi n over square root of n squared, you have 2n squared minus 1, and from 1 to plus infinity is divergent. So let me put it here. Is divergent, which means that the original series is conditionally convergent. So the series cosine pi n over square root of 2n squared minus 1 n from 1 to plus infinity is conditionally convergent. Okay. So for this problem, we want to find the radius and interval of convergence of this power series. So usually our technique in order to find the radius and interval of convergence is the use of limit comparison test. So to do this, we take this guy here. We let this to be our a sub n, and then we find the limit as n approaches plus infinity of a sub n plus 1 over a sub n in absolute values. So in here, this is just the limit as n approaches plus infinity of x minus 2 to the n plus 1 over square root of n plus 1. Then we have 3 to the n plus 1. And then let's just multiply this to the reciprocal of a sub n. The reciprocal is just square root of n, 3 to the n, over x minus 2 raised to n. Then we close this absolute value. And let's work on this completely. So what we're going to do is to separate the x minus 2 from the x minus 2 to the n. And also, we separate the 3 here from 3 to the n. So we will get x minus 2 to the n times x minus 2 divided by square root of n plus 1, 3 to the n times 3. And then here we just copy so that we will have square root of n, 3 to the n over x minus 2 raised to n. And from here, we clearly see that we can cancel x minus 2 to the n. We can also cancel 3 to the n, okay? And therefore, we will be left with the following expression. First, x minus 2 here does not depend on n, so we can bring it out. Also, this 3 here. So we will have absolute value of x minus 2 over 3 times the limit as n approaches plus infinity, square root of n over square root of n plus 1. Or this guy here, uh, let us just combine this into a single radical. So if we do that, this expression becomes square root of n over n plus 1. But anyway, as n approaches plus infinity, the one inside here will just go to 1 because the numerator here it's degree 1, the denominator here is also degree 1. So we'll just get the leading coefficients. So this is equal to 1, and therefore the limit of a sub n plus 1 over a sub n is just absolute value of x minus 2 over 3. And we want this to be less than 1, which gives us what? The radius of convergence. Radius of convergence is r equals 3. So that's coming from this inequality. Let me write that detail. This inequality implies that the absolute value of x minus 2 is less than 3. So yeah, r equals 3. For the interval, okay, from absolute value of x minus 2 less than 3, we have 1 has negative 3 less than x minus 2 less than 3. Okay? Or this guy here, we will get negative 1 less than x less than 5. So if we add 2 on all sides of the equation, we will have this inequality. So definitely the series is absolutely convergent inside the interval. Okay, in this interval without without the negative 1 and positive 5. We will now verify if the series is convergent at these endpoints. Okay, so when x equals negative 1, we have the series of, or the series from n equals 1 to plus infinity of negative 1 minus 2 raised to n over square root of n raised times 3 to the n. And this will be simplified into the series negative 1 to the n over square root of n from 1 up to plus infinity. Okay? So now, let me label this as star. Now, star is an alternating series. So we apply alternating series test. We check all the conditions. So the first condition, the series or the sequence 1 over square root 1 over square root of n is non-negative. Non-negative for all n greater than or equal to 1. Also, as n increases, 1 over square root of n decreases. So decreasing. And finally, the limit of 1 over square root of n as n approaches plus infinity, this is equal to 0. Therefore, by alternating series test, the series negative 1 to the n over square root of n, 3 to the n, and from 1 to plus infinity is convergent. Okay? Next, let's find whether this series is convergent at x equals 5. So when x equals 5, we'll get the series negative, or we have here 5 minus 2 raised to n over square root of n, 3 to the n, as n runs from 1 to plus infinity. But this will be simplified into 1 over square root of n, and from 1 up to infinity, which is a p-series with p equals 1/2, which is less than 1. So that series is divergent. So this series 1 over square root of n is divergent. Let me just write n runs from 1 to plus infinity. Therefore, the IOC, or the interval of convergence, is We include -1 since we have here the conclusion convergent, okay? But we exclude +5. So we have -1 to +5, including -1, but not +5. Okay? Next, we want to find the Maclaurin series for f of x. If we are given the f of x equals 1 over 4 plus x squared. And then letter B, if the Maclaurin series in part A is of this form, we want to find the value, or we want to find the coefficient C sub 26. And then we also use the result in part A to find the exact value of this. So for letter A, remember, we need to, this is what we know. The series x to the n, this is just 1 over 1 minus x, provided absolute value of x is less than 1. So what we're going to do is to write f of x, which is 1 over 4 plus x squared, as 1/4 times 1 over 1 plus x squared over 4. And then if the absolute value of x squared over 4, this is less than 1, then we can write, maybe not if, maybe we should say 4x such that this guy here, we can now write this function using this guy as 1/4 sum from n equals 0 to plus infinity. And by the way, so here we start with 0, okay? And this will be negative x squared over 4 to the n. Or this guy here, it's the series from n equals 0 to plus infinity, negative 1 to the n, x to the 2n over 4 raised to n plus 1. So this is the Maclaurin series for this function. So for letter B, okay, we want to find the coefficient C sub 26. So this means your n equals 0, n equals 1, n equals 2. So we want the subscript of C to be 26. This means we want the exponent of x here to be 26. Okay? But the exponent of x is of the form 2n. Okay? So to find this, we want our 2n to be equal to 26. Okay? That's the exponent that we see here, which implies that your n must be equal to, or our n must be equal to 26 over 2, which is equal to 13. So C sub 26 appears when n equals 13. So C sub 26, this is equal to negative 1 to the 13 over 4 raised to 13 plus 1. And this is just negative 1 over 4 raised to 14. So this is the coefficient C sub 26. Sorry, why did I write this? So it's 4 raised to 14. Yeah, so this is the correct version. And then, finally, for letter C, okay, we want to solve for this from part A. From part A, 1 over 4 plus x squared. This is equal to the sum negative 1 to the n x raised to 2n over 4 raised to n plus 1 and from 0 to plus infinity, provided that uh, absolute value of provided that absolute value of x squared over 4, this is less than 1. So we can take x equals 1. So taking x equals 1, we will get 1/4. This is just the sum negative 1 to the n over 4 raised to n plus 1 and from 0 to plus infinity. So meaning this sum here, it's equal to 1/4. So this is what we need. Next problem, find the Maclaurin series for f of x equals e to the 2x, then approximate the value of e squared to 3 decimal place of accuracy. So this is what we know. Recall e to the 2x or e to the x. Let's write e to the z. This is equal to sum z to the n over n factorial n from 0 to plus infinity for all x in R. So take z equals to x, e to the 2x. This is equal to the sum from n equals 0 to plus infinity of 2x to the n over n factorial. Here, sorry, this guy here should be z. So in here, well, we can just write x in R. But this guy here, we can rewrite this as the sum from n equals 0 to plus infinity of 2 to the n x to the n over n factorial. Now, let us approximate the value of e squared to 3 decimal place of accuracy. So, to do this, let's start with the following. We let, say, p sub n of x. We let this one be the nth degree polynomial, nth degree Maclaurin polynomial for the function f of x. And then, of course, we define the error, define r sub n of x to be equal to f of x minus p sub n of x. Then, according to the theorem, we need to find n such that um, the absolute value of r sub n of 1, this is less than capital M over n plus 1 factorial, okay, times the absolute value of x raised to n plus 1. But by the way, your n here, your x is equal to 1. So this one here it's no longer present. Okay? And we want this to be less than or equal to 0.0005 because we want 3 decimal place of accuracy. So 3 zeros and then the 5 here. Here, where m we can take this to be e f of 1, okay? So the m here, we can let our x to be inside the interval um, between 0 and 1. So where m is some bound, okay? But to be more precise, on the interval 0, comma 1, okay? On the interval 0, comma 1, your e to the 2x will be less than or equal to e squared, correct? So the highest value of x is 1. So 2x will be less than or equal to 1. That's why e squared is less than or e squared is greater than or equal to e to the 2x. But e is some decimal or is some irrational function. So instead of e, let's just use 3. So 3 squared and we will have 9. So what we're going to do, we need to find n such that your r sub n of 1 in absolute values will be less than 9 over n plus 1 factorial, and we want this to be less than or equal to 0.0005. Okay? But this guy here, we mean our n plus 1 factorial would be greater than or equal to 9 over 0.0005. And if we calculate this, we will have 9 divided by 0.0005. This is roughly 18,000. Okay? So we want the n such that n plus 1 factorial equals n 18,000. Okay? And for this, maybe let's just have some trial and error. If we choose, say, n equals, let's see, n equals 8 or 6. Okay, so when n equals 6, when n equals 6, n plus 1 factorial, this is equal to 7 factorial. This is equal to 5,040. Okay, and when n equals 7, n plus 1 factorial, This is 8 factorial, and 8 factorial, it's equal to 40,320, which means we have to take this guy, n equals 7, because this one will be greater than 18,000. If you chose n equals 6, we'll just get 5,040. So we take n equals 7. So we take n equals 7, okay? Which means that e squared, okay? Let me just put it on the next page. So the sum of, what was that again? This guy with n equals, with x equals 1, and we just run n up to 7, okay? So the sum, 2 to the n over n factorial, and from 0 to 7 is approximately equal to e squared with 3 decimal place accuracy. 3 decimal place accuracy. So this is now the sum, or this is now the answer. So that's the end of our review session, and good luck on your exam. Bye-bye.